Well, good afternoon. My name is Dwayne Brown with the Office of Public Affairs. Welcome to NASA headquarters and Happy New Year. Today's briefing features information about the crown jewel in a fleet of NASA missions to study our sun, the Solar Dynamics Observatory, or SDO, which is currently scheduled to launch in February. Today, you'll hear about the advanced spacecraft and the extraordinary science expected. We'll start here at NASA headquarters and then switch to the Kennedy Space Center, where all the pre-launch activities are taking place. We'll have brief presentations from both locations, then open it up for questions. Before we get started, let me introduce you to our participants first here at NASA headquarters. Richard Fisher, Heliophysics Division Director, NASA headquarters here in Washington. Madhulika Guhatakirta, or as we like to call her, Lika, the SDO program scientist, also here at NASA headquarters. And switching down to Kennedy, Dean Pesnell, the SDO project scientist from NASA's Goddard Space Flight Center in Greenbelt, Maryland, and Elizabeth Citron, the SDO project manager, also at Goddard. So with that, I'll turn it over to Richard.
Okay, thank you very much, Dwayne. It's a great pleasure on my part to be with you here today. Let me start at the very center of our issue. At the beginning, at the center of our solar system, there's a star, and this star is a magnetic variable star, and it drives the Earth and all the planets. And it also sculptures space, and through that time and place, there are also transients. If I could have the first video, please. Now, at the dawn of the space age, when NASA was born, there were two crucial experiments. The first one, the very first science experiment that NASA had, established that the Earth was enshrouded by a belt of charged particles. A couple of years later, Mariner discovered that there was a solar wind, a wind that was blowing off the star. And at that point, we had discovered and codified two important things. One of them is that particles and fields are ejected by the sun. And these are two of the ways that the sun, or a star, communicates with the universe. Now, we've been looking at pictures of an active sun taken a few years ago. And we will occasionally see little sparky things that look like snow. And those are charged high-energy particles going through the detectors. Now, the research and the events have led to the development of a study, a formal study, of the interaction of gravity, pressure, and magnetic fields. And this is called heliophysics, a relatively new science. The research benefits from this have proven to be not only of value culturally and intellectually, but they have some research benefit and value to our society in the sense that they are politically important and they have economic impact. And these impacts are on our modern society, both civil and military. Now, as a consequence of our last decade of research in space, we are today poised at the beginning of a new magnetic activity cycle. And let me have the last slide, if I could, please. And we were able to study the sun and its activities inside and outside, its ejections as they go forward out of the sun's atmosphere. And then you can see the Earth enshrouded in this protective blue magnetic field over on the right-hand side. Our spacecraft are used to study this system. It's a systemic investigation. And the SDO is the cornerstone foundation mission for the next decade of solar research. Now, to tell you more about SDO and its program, I'm going to turn this over to Lika, and she's going to talk about Living with a Star program and SDO.
Thank you, Dick. We live in the extended outer atmosphere of the sun. And in that sense, we truly live with this star. Even though to the naked eyes, the sun appears to be a constant pale yellow ball, the sun, it's only a limitation of human eyes. The sun is really not a constant. In fact, modern telescopes and spacecraft have really penetrated the blinding glare of the sun and have found sort of a maelstrom of unpredictable turmoil. As Dick mentioned, and I want to repeat this, the sun is a variable star. It is a magnetic variable star, and this magnetic variability drives every cubic inch of space in this solar system. While sunlight enables and sustains life, the sun's variability produces streams of high-energy particles and radiation that can harm life and even alter its evolution. If I can have the first movie, please. What you're going to see here is a cloud of plasma that's breaking away from the solar surface. These are called coronal mass ejections. It's really charged particles that will travel at tremendous speed, sometimes millions of miles an hour, and go through the interplanetary medium, impinge on Earth's magnetosphere. The blue lines that you see are imaginary field lines, which gives you the shape of the cocoon of Earth, which is the magnetosphere. Most of the time, these particles do not penetrate Earth's environment. They are deflected by this shield, the cocoon. But every once in a while, when the field of sun and Earth are just aligned right, these particles will actually propagate through the poles of the north and south poles of the Earth. And what you see are these particles going in, and they will create beautiful aurorae, both in the north and in the south. That's the beautiful aspect of these particles. But it can also produce harmful effect in our space environment, and I'll talk about that just shortly. So what you can see from this movie is that the origins and fate of life on Earth are intimately connected to the way the Earth responds to the sun's variations. Recognizing this importance, in 2001, NASA initiated a program called Living with a Star, whose goal is to study the sun as a variable star and its impact on life and society. If I can get the next impact slide, please, and talk about what is the rationale behind studying this sun. After all, it's an ordinary star. If you look at the upper half of this slide, what you will see is this variability that we talked about, what it does to Earth's magnetosphere, ionosphere, mesosphere. Wherever there is magnetic field, the sun really dominates that environment. This variability affects every planetary environment in the solar system. And of course, we are really looking at the basic plasma physical processes. And these are universal processes of heliophysics that Dick talked about. And that's what we are trying to understand. It's true for everything we do, I think, in the universe. The lower half of this actually shows the impact of this variability on Earth, what happens there. We have increased dependence on space-based systems. I mean, that's very clear. Our modern way of life is just intimately connected to technology that is driven by this solar variability. Solar variability, as you can see, can affect human in space, satellite operations, smart power grids, GPS navigation, emergency radio communications, air travel, financial services, you name it, and I'm sure we can find a chain that connects it to the sun, and also terrestrial climate. Thus, understanding solar variability is crucial to our modern way of life, which depends on it. So I want to say two things about the mission Solar Dynamics Observatory. SDO is the solar variability mission. It is going to revolutionize our view of the sun, and it will reveal how solar activity affects our planet and help us anticipate what lies ahead. SDO is designed to probe solar variability unlike any other mission at NASA or even internationally. It will observe the sun faster, deeper, and in greater detail than any previous observations, breaking barriers of time, scale, and clarity that have long blocked progress in solar physics. And I'm going to pass it on to Dwayne now.
Okay. Thank you, Richard and Lika. Now we're switched down to the Kennedy Space Center, where Dean and Liz, go ahead.
All right. Thanks, Dwayne. I'm Dean Pesnell, the project scientist of SDO. Together with our science team partners at the University of Colorado, Stanford University, and the Lockheed Martin Solar and Astrophysical Laboratory, we will run SDO, analyze the data, and produce the science of SDO. So I'm here today to talk about some of the science we will do with the instruments. First, let's look at an image of the spacecraft. Here we see the helioseismic and magnetic imager, HMI, the atmospheric imaging assembly, AIA, and the extreme ultraviolet variability experiment. As our sun affects our life more and more, as we come to depend more and more on technology, most of these effects come from the ever-changing magnetic field of the sun. SDO is designed to study that magnetic field from its creation to its destruction and how it then can affect the Earth. Predicting this magnetic field is one of the goals of SDO and Living with a Star, where we use helioseismology to study the movement of material inside the sun that creates the magnetic field in the solar dynamo. Here we have a picture of small changes in the rotation of the sun that were produced by a study of the sound waves rippling across the sun. One bright band moves towards the equator in both hemispheres. In the past solar cycle, we noticed that active regions or sunspots appeared only in and above that band. We will use HMI to make measurements in the upcoming solar cycle to see if that allows us to predict the timing and magnitude of upcoming solar cycles. We will also use HMI to study the surface magnetic field of the sun. Here is an image of the historical information we have. Unlike this image, which only shows the strength of the magnetic field, HMI will also measure the direction of that field. Scientists feel that knowing the direction of the field will help us to make better predictions of when flares and coronal mass ejections will occur. Once the field is out of the surface, we see the field illuminated by hot gas that is forced to flow along the field lines. Here we have two images from the SOHO spacecraft. On the left, we see an image that shows material at a temperature of 1.5 million Kelvin. On the right, we see three different temperatures combined using false colors to show the many temperatures that exist on the surface of the sun. We hope to use AIA to measure the temperature more accurately, and that will allow us to determine how much material is glowing and therefore produce better predictions of flares and coronal mass ejections. The field changes very rapidly in time and quite significantly in space from across the disk to the smallest size we can measure. Here is an animation where we start with a full disk image from SOHO, zoom in on a patch of the sun, and then compare the SOHO view with a higher resolution image from the TRACE satellite. We see far more detail in both time and space with the high-res version. Based on this type of animation, AIA was designed to return high-res versions of the entire disk, allowing us to zoom in on any part we want without having to sacrifice the ability to look at all parts of the sun. The third instrument, EVE, measures the extreme ultraviolet emissions of the sun, which create the ionosphere and are involved in many space weather applications. Here is an example of what those emissions look like during the decline of solar cycle 23. The C instrument on time measured these since 2002, but only every 90 minutes. We now know that we should measure them much more quickly at a pace that matches more what we want to understand for these important emissions. Our data will be made available through our website at sdo.gsfc.nasa.gov, which we encourage you to visit. And now, thank you. Liz Citrin will tell us about our preparations for launch.
Thank you, Dean. After completing more than 6 months of environmental testing and performance verification at Goddard, SDO was packed up and shipped to the launch site processing facility by truck. We arrived in the rain. SDO is processing at Astrotech, a commercial processing facility about 10 miles from Kennedy Space Center. After arrival and waiting out the storm, SDO's moved into a clean room at Astrotech for final testing. You see, we need to make sure that the observatory survived the trip down to Florida without any problems. To do this, we repeat what we call our comprehensive performance test. It's a 7-day test where all elements and components of SDO are verified to be operating correctly. This next photo shows SDO in its test configuration. We're horizontal so that we can shine light into the instrument telescopes. Another step in our testing is testing our deployment mechanisms. Here you see our high-gain antennas being deployed. We also deploy the solar arrays, and we pop the doors on the instrument telescopes. After we've confirmed that everything is okay with SDO, we fuel. This is a 6-day hazardous operation performed by trained personnel in scape suits, protective suits with their own air supplies. And at this point, we're ready to start our integrated flow with the rocket. We're launching on an Atlas V rocket. This photo shows the Atlas rocket already stacked at the VIF, the Vertical Integration Facility. The photo shows the Centaur's second stage being lifted onto the Atlas booster. And that's where we are right now in the flow. The next step for SDO is encapsulation. This is occurring right now at Astrotech. Then, protected by the fairing, SDO will be transported to the VIF and lifted on top of the Atlas stack and mated to the rocket. After a couple of weeks of testing and final closeout activities, we launch. SDO's launch date is February 9th at 10:26 in the morning. If we can't launch on that day for weather or some other reason, we'll try the next day. SDO can launch pretty much any day of the year. Let's watch this animation of launch in early orbit. Here's SDO in the fairing on the rocket. The rocket's on the pad. Ignition, liftoff. The Atlas first stage takes us through the boost phase and then falls away. The second stage Centaur burn starts right before fairing jettison, about 4 minutes into flight. We stay on the rocket for almost 2 hours. Then the Centaur points us in the right direction, burns again, and we separate from the rocket. This is a critical time for SDO. We must deploy our solar rays and point to the sun quickly to get power to our spacecraft. Then we breathe a sigh of relief. We have a 2-month commissioning period where we methodically test all of the spacecraft components and our instruments. Also at this time, SDO is using its propulsion system to move into our geosync orbit. Finally, SDO is fully checked out. We're on station, we're pointed at the sun, and we're sending back amazing data and images of the sun at the rate of 1.5 terabytes per day. Unbelievable. And we're going to do this for 5 years or more. We can't wait for this data to start flowing. Thank you.
Okay, well, thank you all. And we're going to open it up for questions, but I would like to make one statement. We talk about diversity here at NASA, and we certainly take that very seriously. And I've had the pleasure to work with some incredible science teams and project teams at the Science Mission Directorate. And the SDO team is extremely diverse and probably one of the more diverse teams for NASA project. Of course, you've met Lika and Liz. I also want to acknowledge in the audience the program executive at SDO, Dana Brewer, sitting here at NASA headquarters. And certainly as we move forward to launch, you will get to hear more from this incredible team. And I am looking forward to the diversity and also the incredible science with this mission. So with that, we're going to open up for questions on our phone lines, and we will see where we need to go here. I have on my screen here from one of the space.coms, and I believe this is for Dick. For you, after SDO, what's up next in the heliophysics portfolio?
Well, that's a good question for me. Thank you for asking me. After SDO, we have a second mission for the LWS program called Radiation Belt Storm Probes, RBSP. And that's a back to the Van Allen belts mission. We're going to try and resolve some of the ambiguities of space and time with a 2-spacecraft mission that will be going through the magnetosphere at the same time SDO is observing. So our hope is to see cause and effect. Now beyond that, that's to be launched in 2012. Beyond that, in 2014, we're going to have a physics investigation of the day side of the Earth where the magnetic field of the Earth and the magnetic field of the sun mix. And there's a process there that we think may be a universal process throughout the universe that we may be able to test there because that's the laboratory we have. And this is called reconnection. And reconnection is where two fields touch and you turn magnetic energy into heat and light all of a sudden. And so this is what we're interested in up toward after this mission. And heliophysics, as Dwayne says, science never sleeps. This is a physics study which has not only knowledge at the output, but also utility. And I'd like to remind the audience that heliophysics is the science of space weather.
And I just want to take us beyond 2014, that we have some other missions actually in planning stages right now. They are not quite in development stage like Radiation Belt Storm Probe or MMS. We have a NASA, all NASA mission called Solar Probe Plus. And this is a mission that's actually going to visit the sun. It will be in the corona, the eclipse pictures that we see, it will be in that vicinity to actually really sample the material there instead of doing remote sensing observation. We also have a notional mission right now, which is in partnership with European Space Agency called Solar Orbiter, which will be out of the ecliptic and about 0.25 AU, really giving us a different perspective of the sun.
Okay, I have a couple of more space.com questions on my screen, but we're going to go to the phone lines now. And first up will be Rachel Cortland from New Scientist. Rachel?
Yeah, hi. I'm sorry if you're going to be repeating yourself, but the phone line cut out for a while. I was wondering if you could say what the overall cost of the mission is, and also if you could explain in more detail what SDO will be looking at and its capabilities compared to previous orbiters, how it's going to improve things.
Okay, Dick, you want to start that, and then maybe Dean and others can chime in with the science.
Well, I can take a cut at your costs. The SDO mission had a final confirmed price of, I think, about $808 million. We've had a slight delay, and well, it's a considerable delay, and we put money into maintaining that. So I think that the cost to complete plus the science investigation is going to be around $848 million. Now, Dean really needs to comment about the comparison, because the comparison of SDO to previous missions is really fantastic.
Yes, thanks, Rachel, for your question. Let me talk about the extreme ultraviolet images. That's probably the place where we make a largest impact on a difference. When we look at the SOHO instrument, we measured things on a certain size detector, 1,000 by 1,000 pixels. We're going to be measuring them on a 4,000 by 4,000 pixel detector. So that's the first difference, is we're going to be able to see smaller features within the full disk images. But the most significant change is simply going to be we're sending down so many more images of the sun. We're going to send down an image from AIA every 1.25 seconds. If we look at the comparison with SOHO, the best was about every 12 minutes. And if we look at the stereo spacecraft, which is orbiting the sun now, it would be about every 3 minutes. So we're looking at things in a much higher time cadence. And what we've noticed with other spacecraft that ran at these higher cadences is that the sun changes every time we look at it. The sun's never the same. So when we take these pictures every 1.25 seconds apart, and then we compare them with the same wavelength every 10 seconds, we're going to see that the sun changed in the pictures. We'll also be able to start with the full size of the sun and then go down to the smaller scales without having to get rid of the information from the full disk. So when we look at satellites such as the TRACE satellite, the TRACE was able to look at very high resolution pictures. As a matter of fact, we used that in the animation I showed, but it only could look at one small part of the sun. With AIA, we'll be able to look at the whole sun and zoom in on the interesting bits. Now, we also have an instrument called HMI, which is a helioseismic magnetic imager, and that builds on the SOHO spacecraft MDI instrument, and it also builds on stuff that we've derived from the GONG network on the ground. What we learned from MDI was we can't do the onboard processing of the data to do a data compression to make it easier to send it to the ground. We really need to get all of the filtergrams, the actual pictures of the sun, so that we can send them down and study the sound waves from scratch. And that is why we're in the special orbit we're in, so that we can maintain the constant contact with the spacecraft. And then the third instrument builds on the EVE instrument, builds on the fact that the C instrument on timed was designed more or less to make daily measurements of the extreme ultraviolet irradiance of the sun. And we learned very quickly that that was just not adequate. We really needed a much higher time cadence for those measurements as well. So EVE is going to make a measurement about every 10 seconds. Does that address your concerns?
I believe it does. Thanks, Dean. We'll take the other question. Next question is from Clara Moskowitz from space.com. Clara?
Yes, hi. You all mentioned that SDO will help predict solar flares, and I'm wondering just what are some of the specific unanswered questions scientists have about what causes solar flares, and which part of the data from SDO will help answer these questions?
Well, you've got a situation here where you've got three scientists, and so you're going to get a batch of answers. But I think that the circumstance that I would remark about is that we have temporal and spatial resolution that I have never seen before available. And I think as far as unresolved questions go, we're going to add some physics to that by having a vector magnetic field along with it. So I'm going to toss this toward Lika. I think it'll take all the instruments to do a better job on flare prediction and flare effects, and that's why they've been chosen. So they work in concert.
And when Lika would then toss it down to Dean to get the third scientist view. Okay.
And it's not just SDO instruments, I would add, as Dick had noted earlier. I think we need all our observatories to make fundamental progress on the system science of heliophysics. I think the vector magnetic field is going to provide tremendous insight, because we really need to understand the geometry. When we are modeling, that geometry is critical. I think with HMI, we are actually going to be penetrating deeper into the magnetoconvection zone, which is kind of the seat of dynamo, the heartbeat of sun. And you know, understanding the dynamo, being able to predict that is sort of the holy grail of solar physics. And I think SDO is going to make a tremendous progress on that. I mean, that's why we have this huge amount of data being beamed back to us almost 24/7, and we want all of it all the time. These are just some of the ideas. I'm going to pass it on to Dean, who's been managing all these science issues for now quite a while.
Okay, thank you, Lika. We have all three instruments on SDO will be involved in trying to understand how to predict flares and also coronal mass ejections. It's been an outstanding question for quite some time in solar physics, and we've made some progress. We have people that can predict flares some of the time, but we need to do a better job. We're going to use the magnetic field from HMI as one component of that, and especially because we'll have the direction, so we'll be able to see that the magnetic field, not just its strength, but we'll be able to see how much it's gotten twisted up. Is that part of predicting flares? We'll be able to measure the temperature of the gas in the AIA images, and from that know whether or not there's a lot of material. Is it the amount of material that's showing up that is one of the significant parameters we need to look at? And we'll also have EVE. EVE will tell us how much energy came out of each of the flares. And we already know from the C instrument on time that not all flares are the X-ray flares that everybody's familiar with. There's other types of flares that are a little less energetic. Are those the ones that we really need to study? Is that the real background that we need to understand? So all three instruments working in concert will allow us to understand the onset and energy release inside of flares.
Thank you, Dean. Now we will go to the next caller, which is James Dean from Florida Today. James?
Hi, thank you very much. For our headquarters panelist, I was wondering if you could just talk a little bit more about the vulnerability of spacecraft and some of the other modern systems you mentioned, like the power grid, to these high-energy particles. Could you cite any incidents where this type of damage has occurred and how common it is? And also, is it something that generally can be protected against in some effective way, or how would SDO's investigation help reduce that vulnerability?
Well, I can start on that, but I think that it may take some help from Dean or from Lika. In the past, the issue has been charging of spacecraft from the standpoint of they collect a lot of electrons on the outside, and you get a charged spacecraft, it discharges through it. And so you can partially mitigate that by construction. You can also partially mitigate that by shutting it down. So if you have knowledge, this is a case where you can take action on the basis of knowledge. This is actually fundamental space weather. The other place that there are impacts are in communications and navigation. Half of the communications of the Earth are still in high frequency radio transmissions. And these are modulated by the ionosphere flapping up and down, and it changes the path length. And this has been known since the beginning of radio. And the communicating from some place to someplace down on the equator has this problem. And if you can forecast that, you can choose some other thing, you can do it. Now, power grids are something that have grown up, intercontinental energy transmission lines, or things that have grown up over the past 50 to 100 years. And they're conductors that are on top of a magnetic field. So when we have a big blast of particles, a conductor moving through a magnetic field generates a current. And there are currents that are generated which are so large that they will damage transformers. Now, we have so many power systems linked together at the present time that they run dependently upon each other. And if one goes down, the other one tries to pick up the load, the other one picks up the load, blah, blah, blah. And somewhere you have a little glitch that shorts out a transformer, and it takes down a great big part of the power system. And this has been studied by the National Academy of Sciences, and it's thought to be that it is a certain likelihood that a couple times during a solar cycle we'll have something called a GIC. And this is kind of a funny word, but it's a ground-induced current. And they're solar-induced on the Earth. And these, if you have knowledge that such a thing is likely, you can adjust the power system to avoid difficulties. I'm sure I've left out other things.
Lalika, why don't you, and then we can toss it to Dean.
Actually, you covered a lot. I think I was just thinking, what have you, aircraft. So high altitude aircraft, polar routes, these particles that you see, when these particles actually enter Earth's magnetosphere, I mean, if these are high energy particles, they'll have radiation effect, or single even upset, or it causes communication disruption. So your high altitude aircraft will be affected by these particles. The other effect of these high energy particles, galactic cosmic rays, which is again kind of varies with the solar cycle, is of course it directly affects human in space, especially human if they are not protected by Earth's magnetosphere. So when we are thinking of voyages to moon or beyond to Mars, I think prediction of these high Z particles becomes really very, very important.
Dean, you want to add before we take the next question?
Yes, I would like to just add one area of interest, especially here at NASA, and that is satellite drag. The sun, when it's more active, causes the drag, the upper atmosphere of the Earth to expand, increasing the drag on satellites and basically bringing them out of orbit. In this past minimum that we've had, the Earth's atmosphere has actually contracted so much that we're in a period of time unlike any before. We're not seeing any drag on the satellites. And worse than that, we've had major amounts of debris left in our low Earth orbit satellites, and we're not cleaning that debris out. So the satellite drag is very important for NASA and for other people that operate satellites, especially in low Earth orbit. And I think that would be all I'll say.
Okay, I'll go to the my screen here. I believe this is for Dean. Question: when do you expect the first data or images, if any, to come down from the spacecraft once it's checked out?
We get about 30 days to move the orbit into geosynchronous orbit. We're in an inclined geosynchronous orbit at the longitude of New Mexico. And so we are in constant contact with the spacecraft. And it takes about 3 weeks to 4 weeks to get into that orbit. At that point, we start opening the doors on the instruments and start doing our tests of the instruments to make sure that they made it into orbit and are doing fine. And we get about another 4 weeks. So about 60 days after launch is when we expect to be able to release science data.
Okay, my last question here on the screen, and this is a question for everyone. So we're going to start with Liz, Dean, and then come up with Lika and let Dick have the final words. But the question is, what are each of you all's personal thoughts after waiting for the launch and feeling that you're very close to launching the crown jewel of heliophysics? Your personal thoughts on that. And we'll start with you, Liz, and then Dean.
Okay. Well, Dwayne, I have mixed feelings. This is my baby, and it's very hard for me to push it out on its own. So, but I'm proud that it's my baby. I know it's going to perform. I know it's just going to be wonderful. So, as I say, mixed feelings, anxiety and pride. Dean?
Okay. Well, we're just waiting. We know how much SOHO and other spacecraft have revolutionized solar physics. SDO has been designed to take advantage of what we learned from those missions. And I see this as a revolutionary mission, and the data that SDO produces in 5 to 10 years, we're going to be looking back and just amazed at what we learned from it. So I'm waiting to be amazed.
And Lika?
Well, I think my emotions are also kind of mixed like Liz's. I think I have been part of Living with a Star from its inception. And to see actually the first mission of this program, happen is just exciting. And I think I feel really fortunate. It's not very often that it happens in one's career that you can be part of a concept and then actually go through the process of building the spacecraft, launch it, wait for data, and see the results of exciting science and really entering the next generation, I think, of heliophysics.
And Dick?
Well, I'd have to echo the things that people said, but I think it should be noted that this team, in my opinion, is the very best in the world. And for me, it's been an enormous privilege to be involved from the beginning, and I'm very grateful for that opportunity.
And that's going to wrap it up. It's always good to end on really passionate personal feelings on the SDO launch and its mission. I want to thank you all for joining us. I also want to mention that there are some incredible education and outreach activities that will be taking place before the launch, so we can check your website at www.nasa.gov. This is an incredible team. Stay tuned for the crown jewel. And Dick already said it, but I've got to end it here. When it comes to studying the sun, science never sleeps. Thanks for joining us, and we'll see you in February.